When we're dealing with a precipitation reaction, one of the ways that we often represent it is with a few different styles of equations. And so we have what's called a formula equation, which is the one you're very familiar with. There's also what is called the ionic equation, which shows every ion in an entire solution. And there's what's called the net ionic equation, which ultimately just represents the change in a solution. And so to look at this, we are going to take a look at an example where we're dealing with some compounds that are reacting. We'll predict the precipitation and write out these three styles of equations. So in this, we have lead nitrate reacting with sodium iodide. And one of the most important things that we're going to do is make sure we have our states. And since this is a double replacement, we have two aqueous substances right at the start. Then what we're going to do is predict our precipitation. And so we need to look at what substances might form after the reaction. Since it's double replacement, the positive lead and the positive sodium are going to switch what they are paired with. So the lead is going to pair with the iodine. So you get Pb, and it's going to be I2 because Pb has a positive 2 charge, I has a -1 charge. The other substance you end up getting here is NaNO3. Na has a single positive charge, and NO3 has a single negative charge. Now, we want to balance this equation. I have two NO3s and only one NO3 here. So I'm going to balance that with a 2. That gives me two NAs. So I need to balance that with a 2, and that gives me two I's, and here I have two I's. So now I need to check the solubility of these two substances. So you would check on your solubility table. You would find that anything with a nitrate is soluble. So sodium nitrate is going to be aqueous. Lead iodide, so iodide combined with either silver, lead, mercury, or copper 1+, that's low solubility, meaning that it should form a solid. So now that we know that, this representation of this reaction is what we would call the formula equation. It is just the standard way that we write out a chemical equation. But there is another way to write this, and it's what is called the ionic equation. And the ionic equation shows every single ion in an entire solution. So since anything that is aqueous is actually dissociated from each other, it means that we're going to take these two substances that are aqueous and actually split them into their separate ions inside the ionic equation. So what that means is I'm going to get Pb2+, and it's going to be aqueous. And by the way, if you're doing this along, you're going to need a lot of space because there's going to be a lot of things that we write here. We need to have the other ion, NO3, and there are two of them. So 2 NO3. NO3 has a -1 charge, and it's going to be aqueous. Then we need Na and I, both aqueous, so divided and split apart from each other, so dissociated. And keep in mind there's two of each of them. So we have 2 Na plus aqueous, 2I minus aqueous. So this is my reactants. Everything that was aqueous, I dissociated from each other and wrote as a separate ion. Now, the products, anything that is not aqueous actually stays together. It is not dissociated. So that means PbI2 is just going to stay PbI2, and its state is going to be solid. But NaNO3 is aqueous, and we need to make sure it's balanced. So we're going to have 2 Na plus aqueous and 2 NO3 minus aqueous. And as you can see, like, this is huge. I ran out of room on my screen here to show you. So this is what we would call an ionic equation. It has every ion written in it and shows basically what is going on inside of the entire solution. But we would rarely use this. What we use instead, much more often, is what is called the Net Ionic Equation. And the Net Ionic Equation just shows the substances that reacted. And to find this, you want to find, okay, what was my substance that actually changed? Well, that's in this case the PbI2. So after my arrow, I'm going to have PbI2, and it's going to be solid because that's what it turned into. And then we want to find, okay, well, what did it actually react with? Well, the lead 2 plus and the I minus were the things that actually reacted. So Pb2 plus aqueous plus 2I minus aqueous, producing PbI2 minus solid. This is my net ionic equation. You can see it actually just shows the things that totally changed in this solution. It does mean something else here, and that has to do with these substances in this ionic equation. If you notice, the NO3 and the Na didn't really change over the course of this reaction. Well, these have a special name, and we would call these spectator ions. They actually don't really do anything. They're just floating around in the solution, not changing at all. And we know that because they stay the same on both sides of that equation. Spectator ions really just sit by and watch the reaction take place. They're not actually involved in the chemical reaction. So this is how we write out a formula equation and predict our products. An ionic equation with every aqueous substance dissociated from each other. How we write a net ionic equation by identifying the one substance, or possibly two, it is possible to have two, identifying the substance that changed, and then using the substances that made it from the reactants. And how to identify spectator ions by finding the things that don't actually react. So hopefully this example helps you understand how to write these 3 different styles of equations. So thanks for watching.